Good afternoon to another session with me, Sri Lekha, lecturer in mechanical engineering. And today we are going to solve few more problems related to simple stress, strain, and tensile tests. So today's problem: see, a steel rod of 30 mm in diameter and 600 mm long has a permissible stress 160 Newton per mm square. Calculate pull required in kilonewtons and elongation in mm if E is equal to 2 into 10 to the power of 5 Newton per mm square. So it is given that a steel rod which is of length 600 mm and given that its dia it is 30 mm, okay, subjected to certain pull. Okay, now given diameter is 30 mm, so from this you can find area of cross section, that is pi by 4 d square. So this is nothing but pi by 4 into 30 square. So how much will you get this value as? 706.85 mm square. So this is the value that you get by making use of this diameter. Next we are given with L of 600 mm. Now they want pull required as well as elongation in length. So how to calculate this? We need to find out now. So I think this was discussed earlier also. So permissible stress is given, that is sigma equal to 116 Newton per mm square. So now I am taking the formula for stress. So stress is equal to load by area. So that implies, so stress value is 116 and load is not given. You need to find the load, that is pull required in kilonewtons. So that is P by area we found by making use of diameter, that is 706.85. So therefore that implies P is equal to 116 into 706.85. So what value we are going to get by multiplying these two things? It is how much? So we'll get somewhere P is equal to 82 into 10 to the power of 3 newtons. So you can simply write it as, so they asked us in kilonewtons, hence 82 kilonewtons. Okay, so this is our load. We found one thing. So more we need to find elongation in mm if E is equal to 20 into 10 to the power of 5. Now, so I am taking, let delta L be the elongation due to that tensile stress. We know that Young's modulus is equal to stress by strain. Okay, so Young's modulus is already given, it is 2 into 10 to the power of 5. So 2 into 10 to the power of 5 is equal to, so the stress value is already given, that is 1. So 116 by, we know sigma, so strain is simply E is equal to change in length by original length. right? So change in length is the thing which we need to find, and the original length is already given, that is 600 mm. 600 mm. So now if I want delta L, it is simply 116 into 600 by 2 into 10 to the power of 5. So this value you will get it is somewhere around 0.348 mm. Okay. So this is the values that we found. So for this kind of problem you need to calculate like this. Okay, so we wanted steel to calculate pull and elongation for given diameter, length, stress and Young's modulus. So what we have done, first we have taken stress. So from this stress formula you are provided with the area and stress, you need to find load. Thereafter it is given Young's modulus, you need to find change in the length, that is elongation. So we know that strain is equal to delta L by L, and also Young's modulus is stress by strain. So therefore on substituting all the values in this equation, you are left over with only delta L. So that delta L we are found by making use of this. So simply elongation in length is 0.348 mm. Okay, so this is all. Now let us go for next problem. So that is a steel rod of 20 mm diameter and 600 mm long is subjected to an axial pull of 40 kilonewtons. So determine the elongation of rod if E is equal to 100. So again I am taking the diagram here. Say if the steel rod is of dia 20 mm, now it is subjected to an axial pull of 40 kilonewtons and length of this L is equal to 600 mm, and also given E is equal to 2 into 10 to the power of 5 Newton per mm square. Now determine elongation in length. It means you need to find delta L. So let me take first stress. So for given diameter I'll find area of cross section. So the formula is pi by 4 into d square. So it is pi by 4 into 20 square. Okay, so I'll calculate all those and at last I'll write down. So it is this 314.159 I got 159 mm square. Next, so we need to find stress. So stress sigma equal to load by area of cross section. So load is given, that is 40 kilonewtons. I am just taking in newtons. By area is this one 314.159. So this value is 127.32 Newton per square. Okay, so this is the stress value which we obtain. Next, so we want delta L. So strain is simply E equal to delta L by L. So that is equal to, delta L is not known and L is simply 600. Okay, now I am taking Young's modulus or modulus of elasticity is stress by strain. Therefore that is nothing but 127.32 divided by delta L by 600, and this E value is also given already for us. So that E value is simply 2 into 10 to the power of 5. So from that delta L is equal to, you can take 127.32 into 600 by 2 into 10 to the power of 5. So this value will be getting around 0.382 mm. So likewise simple things these are. So first we have written the given data. We have found area of cross section by making use of the diameter. Then after we took the stress formula, load by area, and we know already the load, it is 40 kilonewtons, and area we got already. So from that we found stress. Then after we took strain. So strain is equal to delta L by L, that is change in length by original length. So delta L is the thing which we need to find. So L is 600. So again Young's modulus or modulus of elasticity equal to sigma by E. So this is simply 127.32 by delta L by 600. It is equal to 2 into 10 to the power of 5. This value is also already given. So if you take this entire equation out of this, so if I want delta L, if I am making this as subject, the remaining all calculated value is this one. So the elongation in the length is this. Delta L is equal to 0.382. Right? So this kind of simple problems regarding the stress and strain will be given. And now let us go for tensile test problems. Okay, tensile test problems. In this we have to calculate a number of things. Let us do all this now. So let us go through the question first. The following readings are obtained from tensile test of a specimen. Diameter of the specimen is 20 mm. Gauge length is 100 mm. Extension at a load of 100 kilonewtons is 0.15 mm. And the load at yield point is equal to 120 kilonewtons. Maximum load is 200 kilonewtons. Final length is equal to 170 mm and diameter of the neck is 12.6 mm. Now calculate Young's modulus, stress at yield point, percentage reduction of area, working stress. Percent working stress taking a factor of safety this. So if I repeat it once again. So in the tensile test the salient points lies are, So while you are going for tensile test and you are going on adding, so initially it is proportionality limit. So at this place stress is directly proportional to strain, so where you can make use of Hooke's law. Then after comes elastic limit. So till here it will show its elastic nature only. Next comes yield point. Okay. So from here onwards you go on increasing the load, proportionality limit will be crossed and you will get elastic limit. After that, if you are increasing load, yield point will be getting. So from here, so till here it will show its elastic deformation. Whereas it will show uniform plastic deformation. It means it will not regain its shape after removing the load. So this is very next to that of elastic limit. After that it will go on deforming, uniformly deforming at a maximum weight, that is nothing but ultimate point. At ultimate point what it does, so it will carry maximum load. It will carry maximum load, that is maximum stress can be induced there, induced at this point. Okay, so from here what happens, it will show localized plastic deformation. It means generally at the neck it is obtained, localized plastic deformation. So after that you'll have fracture. Fracture is the place where the specimen breaks simply. Okay, so coming again, so initially you will have proportionality limit, then elastic, then yield, then ultimate, and then fracture. So all these values will be given for a given tensile test. So let us go for our problem back. See here that so the following readings are obtained from a tensile test of a diameter of a specimen. So this is your initial diameter of the specimen. The specimen, it is 20 mm. Next, gauge length is given. Gauge length is nothing but, so initial length or original length, so that is 100 mm. Okay. Next, extension at a load of 100 kilonewtons, it is this. It means the change in the length delta L is 0.15 mm. So where will we get this delta L? So it is obtained in within the elastic limit only. So it means this load comes under elastic limit only. So I'll write load at elastic limit is 100 kilonewtons. Next, load at yield point is given. Load at yield point, it is equal to 120 kilonewtons. Next, maximum load, it is maximum load is nothing but what, this is ultimate load. It means this is the maximum load that will be held by the specimen. Means because of this load it will not fail. After this, when the load it will start localized deformation. Okay. Next, this is maximum load. After this, length after failure. So that is 170 mm. Next, diameter of neck. This is also after failure. This is 12.6 mm. Now, so let us go one by one. So first let us find Young's modulus. So Young's modulus, we know Young's modulus is nothing but E, it is nothing but stress by strain, right? So first I'll find stress. Stress is load by area. So which load you have to take at elastic limit? Okay, so at elastic limit you have to take. Next, so load is, what is the load at elastic limit? So load at elastic limit is 100 newtons. So it is 100 into 10 to the power of 3 by, so area, so at this elastic limit the area you have to consider of the, according to the diameter of the specimen. You should not take this neck diameter. This is after the failure you have to consider. So diameter D is given. So with respect to this, the area is pi by 4 d square. So pi by 4 d square means pi by 4 into 20 square. So this value is 314.159 mm square. So just substituting that only. So 314.159 mm square. So this value is how much? This value is how much? You will get 318.3 Newton per mm square. Next, I want strain also. So strain E is equal to change in length by original length. So we have seen already extension at a load of 100 kilonewtons is 0.15. Original length is 100 mm. So I am just substituting the values. It is 0.15 by 100. So what you will get? It is simply 1.5 into 10 to the power of minus 3. Now I will make using of these two and I will find E. So Young's modulus E equal to stress by strain, that is 318.3 by 1.5 into 10 to the power of minus 3. So what value I will be getting? So I will be getting 2.122 into 10 to the power of 5 Newton per mm square. So I got Young's modulus. My first task is finished. Now the second task is stress at yield point. So I am taking stress at yield point. So we all know formula for stress is simply load by area. So stress at yield point means I have to take load at yield point. So here already it is given in the question, load at yield point is this much. So it is simply 120 into 10 to the power of 3, 120 kilonewtons. So 120 into 10 to the power of 3 we have taken. Area is already known, that is, so here also at yield point also that workpiece is not going to break. So you have to consider the actual diameter only. So this value I will get 120 into 10 to the power of 3 by 314.159. I'll get 381.97 Newton per mm square. So stress at yield point is equal to 381.97 Newton per mm square. So this is my stress at yield point. Now next what I need percentage elongation. So percentage elongation can be got by the formula final length minus original length by original length into 100. Okay, so final length is already given, it is 170 mm, and the original length, gauge length, it is 100. So I'll write 170 minus 100 by 100 into 100%. So it is simply 70. So 170 minus 100 is 70. So 70 by 100 into, so it is simply 70%. So percentage elongation is also 70%. Okay, so this is percentage elongation. You got 70%. Next I want, so as you know, if the length is increasing, then its cross sectional area is decreasing. Percentage reduction in area. So what is the formula for this? The formula for this is percentage reduction in area is equal to original area minus area after failure by original area into 100. So now how can I find this area after failure? See, here you are having diameter of the neck. So diameter of the neck D 12.6 is given. So from this area after failure, I'll find it is pi by 4 into 12.6 square. So this is nothing but area after failure. So how much I'll be getting? It is so I'll be getting it's about 124.69 mm square. Okay, so 124.69 mm square. Now I'm substituting. So the actual area is 3.14.159. So 314.159 minus area at failure is 124.69 by 314.159 into 100%. So this one, how much I will get? So I have to calculate it again. So 314.159 minus 129.69 by 314.159 into 100%. So I am getting for about 60.3%. So this is my percentage reduction in area. It means its area is decreasing by 60.3%, where the length is increasing by 70%. Now next, So the last one, it is working stress. For factor of safety, for a factor of safety of 3. Okay, so we know that factor of safety is equal to simply yield stress or ultimate stress by working stress. Okay, so factor of safety is yield stress by working stress. So yield stress, we already found that stress at the yield point we got 381.97. okay, so now I'll take, so factor of safety is 3 and yield stress is already there, that is 381.97 by working stress. Okay, so therefore working stress, this is nothing but the actual stress at which the workpiece is going to break down. The working stress is simply 381.97 by 3. So is equal to, I think I have to calculate it once again. So 381.97 is equal to 381.97 by